The common wooden pencil resting on a desk and the brilliant diamonds set within a platinum ring appear to be materials from entirely different universes. One is a symbol of utility and disposability, a tool used to record temporary thoughts that can be wiped away with the swipe of a rubber eraser. The other is a global benchmark for permanence, hardness, and extreme luxury, often passed down through generations as an heirloom. Yet if one were to zoom into the molecular architecture of these substances, it would be discovered that both are composed of the exact same ingredient. They are both pure carbon, the sixth element of the periodic table. The radical difference in their physical behavior is not a result of their chemical composition, but of the specific way their atoms are arranged and held together. Carbon is the ultimate shapeshifter of the material world, a substance that can be the softest or the hardest material on Earth, depending entirely on its internal geometry.
This exploration of the elementary building blocks of our reality is part of an ongoing investigation into the hidden mechanics of the universe. Subscribing to the channel and leaving a comment below helps ensure that these deep dives into the fabric of our world continue to reach a wider audience of curious minds. The physical reality of graphite, the lead in a pencil, is defined by a lack of three-dimensional structural unity. At the atomic level, carbon possesses 4 valence electrons, which are the primary tools used to form bonds with other atoms. In the state of graphite, each carbon atom uses only 3 of these electrons to bond with its immediate neighbors in a flat, hexagonal pattern. This results in the formation of vast, two-dimensional sheets that look like a microscopic honeycomb. These sheets are incredibly strong within their own plane, as the chemical bonds holding the hexagons together are robust. However, the connection between the sheets themselves is governed by a much weaker physical phenomenon, known as van der Waals forces. These forces are the molecular equivalent of static electricity, or a very weak temporary glue. To explain this on the fingers, a block of graphite is not a solid, monolithic structure, but rather a massive stack of incredibly thin, slippery notepads. When the tip of a pencil is pressed against a piece of paper, the friction of the stroke is greater than the weak van der Waals forces holding the layers together. As a result, the bottom pages of the carbon notepad simply slide off and remain behind on the cellulose fibers of the paper. This is why a pencil leaves a mark. It is literally shedding millions of atomic-scale flakes of itself. This same slippery characteristic makes graphite one of the world's most effective dry lubricants. In industrial machinery, where liquid oil would evaporate or catch fire, such as in high-temperature locks or bearings, powdered graphite is used to allow metal parts to slide past one another without grinding. The atoms are so loosely connected in one direction that they act as a microscopic carpet of ball bearings. The optical appearance of graphite is a direct consequence of this electronic arrangement. Because only 3 of the 4 electrons are tied up in bonds, the 4th electron is left __quote_3___. It is free to move across the surface of the carbon sheet, much like a thin film of water on a pavement. When light strikes these free-moving electrons, it is absorbed and re-emitted in a way that makes the material appear dark and metallic. Graphite effectively for the visible spectrum, reflecting only a dull, greasy luster. It is a material of shadows, defined by its willingness to crumble and its inability to let light pass through its layers. The diamond, conversely, represents the pinnacle of atomic discipline and spatial symmetry. Within the high-pressure environment of the Earth's mantle, approximately 100 miles below the surface, the same carbon atoms are subjected to temperatures exceeding 2,000 degrees Fahrenheit and pressures greater than 725,000 pounds per square inch. Under these conditions, the loose, layered arrangement of graphite becomes thermodynamically unstable. The atoms are crushed so closely together that the slippery notepad structure collapses, and a new, more efficient geometry emerges. In a diamond, Every single carbon atom uses all 4 of its valence electrons to form equal, powerful bonds with 4 other neighbors. This creates a 3-dimensional shape known as a tetrahedron, a 4-sided pyramid. This tetrahedral structure is the most rigid configuration possible in nature. Instead of independent sheets, the carbon atoms form a continuous, interlocking lattice, where every part of the system supports every other part. This can be compared to a massive, 3-dimensional geodesic dome, or a complex architectural truss, where every steel beam is welded to 4 others. To move a single atom in a diamond, one would have to break the chemical bonds of the entire structure simultaneously. This is why a diamond is the hardest known natural substance. It does not shed layers like graphite. It holds its shape with an uncompromising mechanical grip. While a steel file will slide harmlessly over the surface of a diamond, the diamond can easily carve through the steel because its atomic truss is simply too dense and stable to be displaced. The transparency and brilliance of a diamond are also a result of this perfect 4-electron bonding. Because every electron is firmly locked into a chemical bond, there are no free electrons left to absorb light. Photons, the particles of light, pass through the crystal lattice like a bird flying through a wide meshed fence. However, because the atoms are so densely packed, the light is slowed down as it enters the diamond, a phenomenon known as refraction. When a diamond is cut into precise facets, the light that enters it is reflected internally off the back walls of the stone, bouncing multiple times before exiting through the top. This internal reflection is what creates the fire of the gem. The carbon has transitioned from a material that hides light to one that manipulates it with mathematical precision. The conversion of graphite into diamond in nature is a process that takes millions or even billions of years. It requires a specific geological delivery system, usually a volcanic eruption of kimberlite magma, to bring these deep-seated crystals to the surface before they can be reconverted into graphite by the lower pressures of the crust. This rarity has historically dictated the high price of the stone. However, the modern industrial ability to create synthetic diamonds through high-pressure, high-temperature (HPHT) or chemical vapor deposition (CVD) has revealed that the magic of the diamond is not in its scarcity, but in the specific energy required to force carbon atoms into that tetrahedral handshake. Today, synthetic diamonds are produced by the ton, used in everything from industrial saw blades and drill bits to the heat-dissipating layers in high-power electronics. Carbon's ability to exist as both the "14" and the "15" is a testament to the fact that the properties of matter are emergent. They are not found in the identity of the atom itself, but in the relationships between atoms. This is the concept of allotropy. If the carbon atoms are a group of people standing in a room, they can choose to lie down in flat, unlinked rows, graphite, or they can choose to lock their arms and legs together to form a solid, immovable pyramid, diamond. The people are the same, but the __16__ behaves in a completely different way. This duality is the reason carbon is the foundational element of all life and most modern technology. It possesses a "17" that allows it to form the long, complex chains of proteins and DNA, while also being capable of forming the most resilient industrial structures. When a person writes with a pencil, they are performing a micro-demolition of a carbon structure, leaving behind a trail of 2-dimensional ruins on a page. When that same person looks at a diamond, they are witnessing the result of a cosmic-scale compression that forced those same atoms into a state of absolute 3-dimensional order. Carbon is the silent orchestrator of our physical experience, proving that the distance between "18" and "19" is often nothing more than a matter of atomic geometry and the pressure of time. It is the multiform god of the periodic table, a material that reminds us that brilliance and utility are 2 sides of the same elemental coin, depending entirely on how we choose to organize the connections between the smallest pieces of the world. The existence of carbon throughout the cosmos is the result of a profound and statistically improbable nuclear coincidence that took place in the high-pressure laboratories of ancient, dying stars. While hydrogen and helium were manufactured in the immediate aftermath of the Big Bang, the universe for a long period remained a chemically barren void, devoid of the heavier elements necessary to build planets or biological organisms. The transition from a universe of light gases to a universe of complex matter required the synthesis of carbon. Yet the laws of nuclear physics appear to provide no viable path for its creation. In a standard nuclear reaction, atoms fuse to form heavier elements, but carbon occupied a position on the atomic ladder that was theoretically unreachable. To understand why carbon exists today, one must examine a phenomenon known as the Hoyle Resonance, a cosmic quote, 20 where the fundamental constants of physics aligned with the precision of a master locksmith to permit the birth of the sixth element. In the first 3 minutes of existence, the Big Bang produced a vast quantity of hydrogen, 75%, and helium, 25%, with trace amounts of lithium. However, the expansion of the universe was so rapid that the temperature and density dropped before the heavier elements could be forged. This left the early cosmos in a state of elemental arrested development. To build anything heavier than lithium, nature required the intense heat and density found in the cores of stars. Yet, even within the most massive stars, the production of carbon faced a seemingly insurmountable bottleneck. This is known as the quote, 21 In the core of a star, helium nuclei, each containing 2 protons and 2 neutrons, collide to form heavier atoms. When 2 helium-4 nuclei fuse, they create beryllium-8. This is where the engineering of the universe encounters a critical failure point. Beryllium-8 is a quote, 22 isotope. It is incredibly unstable and possesses a half-life of approximately 10 to the power of -16 seconds. To visualize this duration on a human scale, one can consider it to be the time it takes for a beam of light to travel a distance smaller than the width of a single human hair. The beryllium-8 exists for such a fleeting moment that it almost immediately disintegrates back into 2 helium nuclei. For carbon-12, 6 protons and 6 neutrons, to be formed, a third helium nucleus must strike the beryllium-8 while it still exists. In any standard probabilistic model, the chance of 3 helium atoms colliding in such a narrow window of time is nearly 0. It is comparable to trying to catch a falling snowflake with a second snowflake, and then hitting that pair with a third snowflake, all before the first one melts in the palm of a hand. The resolution to this mechanical impossibility was predicted in the 1950s by the astrophysicist Fred Hoyle, who employed a form of reverse engineering logic. He realized that since carbon is abundant and we are composed of it, there must be a specific quote, 23 or a resonance within the carbon nucleus that makes this 3-way collision successful. This is the Hoyle state, a specific energy level at 7.65 million electron volts. When the combined energy of a beryllium-8 nucleus and a helium-4 nucleus matches this exact value, the probability of them fusing into carbon increases by a factor of millions. This resonance functions like a specialized chemical quote, 24 or a tuning fork. If the energy of the colliding nuclei is even slightly higher or lower than this resonance, the transition to carbon fails, and the star continues to produce nothing but helium and beryllium-rich waste. If the strong nuclear force, the __quote _25 _ that holds the nucleus together, were just 0.5% stronger or weaker, the Hoyle state would shift, the resonance would vanish, and the universe would be a graveyard of hydrogen and helium. There would be no carbon, no organic chemistry, and no rocky planets. We live in a reality where the fundamental numbers of physics are tuned to a frequency that allows carbon to be mass-produced in the stellar furnace. Once this __quote _26 hurdle is cleared, a star becomes a carbon factory. In a massive star that has exhausted its hydrogen, the core reaches temperatures of 180 million degrees Fahrenheit, triggering a state known as the __quote _27 During this phase, the star burns through its helium supply with frantic intensity, converting it into carbon and oxygen. This carbon accumulates in the core of the star, acting as the foundation for the next stages of fusion. However, the carbon does not stay trapped in the stellar interior forever. When these massive stars reach the end of their life cycle, they undergo a core collapse supernova, a cataclysmic explosion that ejects the star's internal inventory into the interstellar medium at speeds of thousands of miles per second. The carbon found on Earth today, in the coal of the crust, the CO2 of the atmosphere, and the proteins of every cell, is the __quote _28 of these ancient explosions. We are effectively constructed from the debris of stars that died billions of years ago. As this carbon-rich dust drifted through space, it was eventually incorporated into the molecular cloud that formed the solar system approximately 4.6 billion years ago. The arrival of carbon on the infant Earth was another exercise in geological luck. During the planet's formation, the Earth was a molten ball of liquid fire. Elements that are siderophilic, or iron-loving, tended to sink toward the center to form the core. Carbon is a volatile and light element, and a significant portion of the Earth's initial supply was likely lost to space or locked deep within the mantle. Yet, a critical mass remained on the surface and in the atmosphere. This carbon was sequestered through the deep carbon cycle, where volcanic activity and tectonic plate movements continuously move carbon between the atmosphere and the crust. On a planetary scale, carbon acts as a global thermostat through the silicate-carbonate cycle. When CO2 in the atmosphere dissolves in H2O, it forms a weak acid that weathers the rocks of the crust. The resulting minerals are washed into the oceans, where marine organisms use them to build shells made of calcium carbonate. When these organisms die, they sink to the ocean floor, effectively locking away the carbon for millions of years. Eventually, tectonic subduction pulls these sediments into the mantle, where the heat and pressure release the carbon as gas, which is then expelled back into the atmosphere via volcanoes. This process functions as a long-term planetary lung, ensuring that the Earth's temperature remains within the narrow range of 32 to 212 degrees Fahrenheit required for liquid H2O and life. The atomic structure of carbon, which makes it so effective at building life, is also a result of its unique position on the periodic table. With 4 valence electrons, carbon is the ultimate socialite of the atomic world. It possesses a degree of chemical flexibility that is unmatched by any other element. It can form single, double, or triple bonds, and it can link with itself to form long, stable chains, rings, and complex 3-dimensional structures. This ability to create molecular skeletons is what allows for the existence of the complex hydrocarbons and carbohydrates that define biological systems. If the carbon atom were any more reactive, its bonds would be too short-lived. If it were any less reactive, it would be as inert as neon. Instead, carbon occupies a Goldilocks zone of chemistry, providing a stable yet flexible foundation for the emergence of complexity.
The cosmic accident of carbon is the realization that the most intimate and essential part of our being is the result of a nuclear resonance that occurred in a dying star billions of miles away and billions of years ago. We are a biological manifestation of a specific energy level in the nucleus of a carbon atom. The sixth element is not just a building block. It is a testament to the fact that the universe is not a chaotic mess of random events, but a highly structured machine where even the most minute shift in a physical constant would result in a total absence of complexity. Every carbon atom in a human's body has survived a supernova, a journey through the vacuum of space, the gravitational collapse of a solar nebula, and the churning of the Earth's mantle. It is a material that was forged in the alpha ladder of a celestial giant and delivered to a cooling planet to become the carrier of genetic memory. Carbon is the bridge between the high-energy physics of the stars and the low-energy chemistry of life, a material that turned the primordial helium wall into an open door for the evolution of the universe. To understand carbon is to understand that we are not separate from the stars, but are their direct chemical descendants, carrying the stellar ash of a nuclear lucky break in every cell of our bodies. This cosmic heritage ensures that carbon remains the most honest and profound biographer of the universe's capacity for order and life. For the greater part of human history, the diamond was regarded as a substance of celestial origin, a material that occupied a category of existence entirely removed from the mundane elements of the earth. In the ancient world, from the courts of India to the palaces of Rome, these stones were valued not just for their rarity, but for a perceived physical immortality. While iron would succumb to the slow, orange rot of rust, and even gold could be dissolved by the most aggressive acids, the diamond remained unyielding, capable of scratching any other surface while remaining untouched itself. This perceived invincibility created a deep-seated philosophical and economic illusion, the belief that a diamond was a divine form of matter, fundamentally different in essence from the soot of a chimney or the charred remains of a forest fire. The eventual destruction of this illusion represents one of the most profound turning points in the history of science, a moment where the historical drama of carbon transitioned from mystical speculation to the rigorous, accounting-based reality of modern chemistry. The architect of this disillusionment was Antoine Lavoisier, a French nobleman and chemist often cited as the father of modern chemistry, though his primary contribution was a ruthless application of logic and measurement to the behavior of matter. In 1772, Lavoisier set out to investigate a claim that had begun to circulate among the more radical experimentalists of the era: the possibility that a diamond, under the right conditions, could actually vanish. To resolve this question, Lavoisier organized an experiment that was as much a theatrical performance as a scientific inquiry, involving a specialized apparatus known as the Great Lens of the Academy of Sciences. This device was a masterpiece of 18th century optics, consisting of two massive curved glass discs, each nearly 4 feet in diameter, with the space between them filled with clear alcohol to increase the refractive power. This burning glass functioned as a solar furnace, capable of concentrating the rays of the sun into a pinpoint of heat that could reach temperatures exceeding 3,000 degrees Fahrenheit. To explain the physics of this apparatus on the fingers, it acted like a giant funnel for energy. Instead of H2O flowing through a pipe, it was the electromagnetic radiation of the sun being compressed into a microscopic area. In this concentrated focal point, the vibrational energy of the atoms in any material placed there would increase so rapidly that the chemical bonds holding them together would be shattered almost instantly. Lavoisier placed a high-quality diamond inside a sealed glass bell jar, positioned exactly at the focus of the lens. To ensure the accuracy of his results, he employed his law of conservation of mass, a principle stating that in a closed system, matter is neither created nor destroyed, only rearranged.
He weighed the diamond and the bell jar with a precision that was unprecedented for his time. As the sun reached its zenith and the focused beam struck the diamond, the observers witnessed a phenomenon that defied centuries of traditional wisdom. The world's hardest material did not melt into a liquid, nor did it shatter. Instead, it began to glow with a brilliant internal light and then steadily diminished in size. It was a slow-motion evaporation of wealth. At the atomic level, the intense heat provided the energy necessary for the carbon atoms to break free from their rigid tetrahedral lattice, the deadly handshake that provides the diamond its hardness. Once liberated, these carbon atoms did not simply disappear. They immediately sought out the oxygen atoms, O2, present in the air inside the jar. This process was a chemical theft. Each carbon atom, C, latched onto two oxygen atoms, forming a molecule of carbon dioxide, CO2. This reaction released a small amount of additional energy as heat, contributing to the combustion. Within a short period, the diamond was gone. In its place remained an empty-looking bell jar containing nothing but an invisible gas. When Lavoisier analyzed this gas by passing it through lime water, a solution of calcium hydroxide, the liquid turned milky and formed a white precipitate of calcium carbonate. This was the definitive fingerprint of CO2. The diamond had burned exactly like a piece of common charcoal, leaving behind the same chemical byproduct as a guttering candle or a dying hearth. The social and scientific fallout of this experiment was immense. To the jewelry-owning elite of the 1770s, Lavoisier's results were a source of profound existential discomfort. The realization that a king's ransom in diamonds was chemically identical to a handful of soot meant that value was not an inherent property of the atoms themselves, but was merely a consequence of how those atoms were packaged. This was the death of alchemical mysticism and the birth of material science. It proved that the universe was composed of a finite set of building blocks, elements, that could appear in radically different costumes depending on their physical arrangement. Carbon was revealed to be the ultimate multiform god, capable of wearing the rags of graphite or the crown of a diamond without ever changing its fundamental identity. The drama continued in 1796 when the English chemist Smithson Tennant provided the final quantitative proof that linked these two extremes of carbon. Tennant performed a weight-for-weight combustion experiment, burning equal masses of diamond and graphite in a stream of pure oxygen. He demonstrated that they produced exactly the same volume of CO2 gas to within the limits of his measurement tools. This confirmed that the diamond was not just mostly carbon, but was entirely carbon. The only thing that separated the soot on a chimney sweep's face from the gems in the royal treasury was the degree of pressure and temperature applied during their formation deep within the Earth's mantle. This realization triggered a century-long obsession with the synthesis of diamonds. If a diamond was just pressurized coal, then it stood to reason that humans could manufacture their own gems if they could only replicate the intense conditions found 100 miles beneath the crust. Throughout the 19th century, numerous scientists and adventurers attempted to tame carbon. Some tried to dissolve carbon in molten iron and then cool it rapidly, hoping the shrinking metal would provide the necessary pressure. Others attempted to use high-voltage electrical discharges to shock graphite into a diamond state. Most of these early attempts resulted in nothing but charred debris and exploded laboratory equipment, as the thermodynamic barrier to creating a diamond is incredibly high. To force carbon atoms out of their comfortable, layered graphite arrangement and into the dense tetrahedral lock requires a level of energy that was beyond the reach of 19th century engineering. The historical drama of carbon discovery thus mirrors the evolution of human perception. We began by treating the different forms of carbon as separate, divine or mundane entities, trapped by our own sensory limitations. We saw the brilliance of the diamond,
and the darkness of the coal and assumed they were opposites. It took the focused light of the sun and the meticulous accounting of Lavoisier to reveal the truth, that the universe is a place of profound underlying simplicity, where a single element can play 1,000 different roles. The tragedy of the diamond, its vulnerability to a simple fire, was the triumph of chemistry. It taught humanity that matter is a fluid, transmutable thing, that the secret of the stars was hidden even in the lowliest of terrestrial materials. Today, this drama has reached its conclusion in the industrial diamond foundries that produce tons of synthetic gems for everything from high-speed drill bits to the heat-dissipating windows of high-power lasers. We no longer view the diamond as a celestial gift, but as a high-pressure carbon lattice that we can manipulate with industrial precision.
Yet the memory of Lavoisier's experiment remains as a reminder of the fragility of perceived value.
Every diamond in existence is technically in a state of unstable exile on the Earth's surface. The lower pressures of the crust mean that every diamond is very slowly, over billions of years, attempting to turn back into graphite. It is a material that is constantly trying to return to the soot, held back only by the immense strength of its own chemical bonds. The historical drama of carbon is the story of how we learned that even the most indestructible objects are merely temporary arrangements of common atoms, caught in a brief moment of crystalline perfection before the laws of thermodynamics eventually call them back to their more humble origins.
The transition of the 21st century from the heavy, metallic rigidity of the industrial age to the lightweight, hyper-connected reality of the digital era is underpinned by a fundamental shift in how humanity manipulates the sixth element. While the historical drama of carbon was defined by the binary opposition of coal and diamonds, the modern, hidden engine of progress is driven by a new category of carbon structures, the nanomaterials. These are substances where the carbon atoms are arranged with a degree of architectural precision that allows them to bypass the traditional limitations of physics. The hallmark of this new era is the material known as graphene, a two-dimensional sheet of carbon atoms that functions as the most efficient conductor of heat and electricity ever identified. To explain this on the fingers, if a standard copper wire is a crowded city street where electrons must constantly dodge obstacles and traffic, graphene is an infinitely flat, empty highway where those same electrons can travel at speeds approaching the limits of physics without ever slowing down. This structural efficiency is not merely an incremental improvement, it is a fundamental reconfiguration of the material world that is currently redefining the boundaries of aviation, energy storage, and microelectronics. The physical reality of graphene is a consequence of a specific type of chemical connection known as sp2 hybridization. In this state, each carbon atom, C, is linked to three others in a perfectly flat hexagonal lattice, creating a structure that is exactly one atom thick. This makes graphene the thinnest possible material in the universe, a substance that possesses length and width, but effectively zero height. Despite this lack of three-dimensional bulk, the carbon-carbon bonds in graphene are the strongest in nature. In a laboratory setting, a single layer of graphene has demonstrated a tensile strength that is more than 100 times greater than that of the strongest steel. To visualize this mechanical disparity, if a sheet of common kitchen plastic wrap possessed the same relative strength as graphene, it would be able to support the weight of a large delivery truck without stretching or tearing. This extreme strength-to-weight ratio is the primary reason why carbon-based materials are replacing metals in the most demanding engineering environments on the planet. The discovery of graphene in 2004 by Andrei Geim and Konstantin Novoselov is a classic example of how a high-tech breakthrough can emerge from a simple mechanical observation. They utilized a technique called micromechanical cleavage, which involved using common adhesive tape to repeatedly peel away layers from a block of high-quality graphite. With each peel, the stack of carbon sheets became thinner until only a single, two-dimensional layer remained. This layer did not collapse or disintegrate. It remained a stable, transparent sheet of atomic chainmail. The reason for this stability lies in the delocalized fourth electron of each carbon atom. Because these electrons are not tied to a specific bond, they form a cloud of charge that floats above and below the carbon sheet, acting as a subatomic stabilizing force. This electron cloud is also what gives graphene its extraordinary electrical properties. In graphene, electrons behave as massless Dirac fermions, meaning they move through the carbon lattice as if they had no mass, allowing for a level of conductivity that exceeds copper by a factor of hundreds. This conductive sheet is currently being engineered to create the next generation of energy storage systems, specifically supercapacitors and lithium-ion batteries. In a standard battery, the speed of charging is limited by how quickly the lithium ions can move in and out of the carbon anode. A traditional graphite anode is like a massive multi-story parking garage with only a few narrow ramps. The cars, ions, must wait in line to enter. Graphene, with its immense surface area and open structure, acts like a parking lot that is only one level deep but spans an entire city. Every car can park or leave simultaneously. By integrating graphene into battery electrodes, engineers are creating power sources that can charge in seconds rather than hours, effectively removing the range anxiety and charging bottlenecks that currently hinder the widespread adoption of electric vehicles. Beyond the realm of pure electricity, carbon has become the indispensable skeletal system of modern transport through the development of carbon fiber reinforced polymers, CFRP. This material is a composite where thousands of microscopic carbon filaments are embedded in a high-performance resin. The manufacturing of these fibers is a process of molecular distillation. It begins with a precursor material, typically a polymer called polyacrylonitrile, PAN, which is subjected to a sequence of thermal treatments. In the first stage, the polymer is heated to 400 degrees Fahrenheit to stabilize it, and then it is moved into a high-temperature furnace reaching over 2000 degrees Fahrenheit in an oxygen-free environment. This is the process of carbonization. Under this extreme heat, all the non-carbon atoms, the hydrogen, nitrogen, and oxygen, are literally boiled out of the structure. What remains are long, continuous chains of nearly pure carbon crystals that are aligned with the axis of the fiber. This alignment is the secret of the material's strength. It is a one-dimensional engineering of the diamond's hardness. These fibers, which are thinner than a human hair, have a tensile strength that can exceed 500,000 pounds per square inch. When woven into a fabric and encased in a polymer matrix, they create a material that is as rigid as titanium, but as light as a piece of plastic. This black gold of the aerospace industry is the primary reason why modern aircraft like the Boeing 787 Dreamliner can fly longer distances with less fuel. Approximately 50% of the Dreamliner's primary structure, including the fuselage and wings, is made of carbon fiber. Because the carbon skeleton is immune to the metal fatigue that eventually causes aluminium to crack after thousands of pressure cycles, these aircraft are safer, lighter, and more durable than any previous generation of flight technology. The hidden engine of modernity also relies on carbon to manage the increasingly problematic issue of waste heat in electronics. As processors become more powerful, they generate a higher density of thermal energy in a smaller space. If this heat is not dissipated, the silicon, Si, will eventually reach its thermal limit and undergo a permanent structural failure. Carbon, in the form of synthetic graphite sheets, is the world's most efficient thermal sponge. Graphite has a thermal conductivity that can reach 1,500 watts per meter Kelvin
in the horizontal plane, which is nearly 4 times higher than that of copper. These carbon sheets are placed inside smartphones and laptops to soak up the heat from the processor and spread it across the entire surface of the device. Carbon is the reason a high-speed smartphone does not melt in a user's hand during a demanding task. It is the silent regulator of the digital brain's temperature. In the realm of environmental engineering, carbon is also the primary tool for purification. Activated carbon, a form of the element that has been processed to have an incredibly high internal surface area, functions as a molecular sieve. A single gram of activated carbon can have an internal surface area of over 32,000 square feet, the size of half a football field. This massive area is covered in millions of microscopic pores that act as traps for contaminants. When H2O, or air, is passed through a carbon filter, the impurities are pulled into these pores by van der Waals forces and held there. This is not a chemical reaction, but a physical adsorption, where the carbon acts like a giant microscopic vacuum cleaner. It is the primary defense against toxins in gas masks, the essential filter in household H2O pitchers, and the industrial standard for cleaning the emissions of power plants. The emergence of carbon nanotubes, CNTs, represents the final frontier of this hidden engine. These are sheets of graphene that have been rolled into perfect, seamless cylinders. A carbon nanotube is essentially a one-dimensional pipe that possesses extraordinary mechanical and electrical properties. They are being explored as a replacement for copper in the billions of microscopic connections inside a computer chip. Because a nanotube is so thin and so stable, it can carry an electrical current 1,000 times greater than a copper wire of the same size, without melting. They are the ultimate wires, the final destination for a civilization that is constantly seeking to shrink the size of its technology while increasing its power. To summarize the modern role of carbon on the fingers, it is a material that has transitioned from being something we burn to being something we build. We have moved from a bulk understanding of carbon, coal, and diamonds to an atomic understanding. We are now architects of the element, using it to create the lightest planes, the fastest batteries, the cleanest water, and the coolest processors. Carbon is the socialite of the periodic table, providing the 4-electron handshake that allows for the creation of infinite complexity. It is the material that has allowed humanity to stop being limited by the weight and rust of iron, moving instead into a world of black gold and silvery sheets. The 6th element is the invisible framework of the present, a substance that proves that the most powerful tools in history are not the ones that are the largest, but the ones that are engineered at the scale of the individual atom. Carbon is the silent driver of the high-speed, high-strength, and high-definition reality of the 21st century. A multiform god that has finally been tamed by the precision of human ingenuity. The role of carbon within the planetary ecosystem extends far beyond its function as a structural scaffold or a source of industrial energy. It serves as the ultimate, unalterable chronicler of the Earth's history. Every atom of the 6th element carries within it a silent record of the era in which it was last utilized by a living organism or trapped within a geological formation. This capacity for bookkeeping is not a result of biological intent, but a consequence of the specific nuclear and chemical properties of carbon's various isotopes. To understand the honest ledger of the planet, one must look at the way carbon functions as an atomic clock, a planetary thermostat, and a deep time biographer. While other elements may oxidize, erode, or vanish into the vacuum of space, carbon remains on the surface and within the crust, cycling through the atmosphere and the biosphere in a relentless billion-year dance that records the rise and fall of entire epochs. This final exploration into the enduring legacy of the multiform element reveals that we are merely temporary participants in a global inventory of matter that existed long before the first cell and will remain long after the final human machine has ceased to function.
The most famous mechanism by which carbon records history is the process of radiocarbon dating, an atomic hourglass that relies on the interaction between the Earth's atmosphere and the high-energy environment of deep space. To explain this on the fingers, the process begins at an altitude of approximately 30,000 feet to 50,000 feet, where the atmosphere is bombarded by cosmic rays, high-speed particles originating from distant supernovae and galactic cores. When these cosmic rays strike a nitrogen-14 atom, the most common gas in our air, they occasionally knock out a proton and replace it with a neutron. This subatomic swap transforms the nitrogen into an unstable isotope known as carbon-14. Unlike the common and stable carbon-12, carbon-14 is radioactive, possessing an extra burden of nuclear energy that it must eventually shed to return to stability. This hot carbon-14 immediately reacts with oxygen to form CO2, which then mixes with the standard CO2 in the atmosphere. Plants breathe this mixture during photosynthesis, and animals consume the plants. While an organism is alive, it is constantly exchanging carbon with its environment, maintaining a ratio of carbon-14 to carbon-12 that perfectly matches the ratio found in the atmosphere at that specific moment. However, the second the organism dies, the exchange stops. The carbon clock begins to tick. Because carbon-14 is unstable, it begins to decay back into nitrogen at a statistically precise rate. Every 5,730 years, exactly half of the carbon-14 atoms in the sample will have vanished. This is the concept of the half-life. It acts as a universal timer. By measuring the remaining amounts of carbon-14 in an ancient piece of wood, a scrap of linen, or a fragment of bone, scientists can calculate with remarkable precision exactly how many thousands of years have passed since that material was part of a living, breathing system. Carbon is the only element that provides this deft timestamp, allowing us to map the chronology of human civilization and the migrations of ancient species with the accuracy of a legal document. Beyond the 50,000-year limit of radiocarbon dating, the element takes on a different role as a deep-time archivist within the Earth's lithosphere. This is the carbonate-silicate cycle, a planetary-scale mechanism that functions as a geological memory bank. When CO2 dissolves in rainwater, it forms a very weak carbonic acid, H2CO3. As this rain falls onto the silicate rocks of the continents, it triggers a slow-motion chemical weathering. The acid eats the rock, releasing calcium and bicarbonate ions into the rivers, which eventually flow into the oceans. There, microscopic marine organisms, from tiny foraminifera to massive coral reefs, utilize these ions to construct their shells and skeletons out of calcium carbonate, CaCO3. This is the process of biological sequestration. When these organisms die, they sink to the abyssal plains of the ocean floor, forming layers of marine snow that eventually harden into limestone and chalk. This massive rock formations, such as the White Cliffs of Dover, are essentially trillions of tons of ancient carbon, archived into the crust of the planet. Each layer of limestone is a page in a stone book, recording the chemistry and temperature of the oceans from millions of years ago. By analyzing the ratio of carbon-13 to carbon-12 in these rocks, a measurement known as the isotopic signature, geologists can determine the state of the Earth's carbon cycle during the era of the dinosaurs, or the first emergence of land plants. Carbon-12 is slightly lighter and is preferred by biological organisms during photosynthesis. Therefore, a sudden shift in the ratio in a rock layer can signal a massive explosion of life or a catastrophic extinction event. The sixth element is the only substance that keeps a census of the biosphere over hundreds of millions of years.
The element also serves as the primary driver of the Earth's long-term climate stability, functioning as a planetary thermostat. While we currently focus on the rapid increase of CO2 due to industrial activity, on a geological scale, carbon has been the regulator that has kept the Earth from either freezing into a permanent ice ball or boiling into a runaway greenhouse state like Venus.
This is a negative feedback loop. If the planet becomes too hot, the rate of chemical weathering increases, pulling more CO2 out of the air and locking it into ocean sediments, which cools the planet. If the planet becomes too cold, the weathering slows down, but volcanoes continue to pump CO2 back into the atmosphere from the subduction of ancient limestone, which eventually warms the planet. We are currently living in a world that is tuned by the movement of carbon atoms between the atmosphere and the mantle. This hidden engine ensures that the Earth remains a habitable laboratory for complexity, proving that carbon is not just a building block for bodies, but a structural regulator for the entire planetary environment. In the contemporary era, the carbon we have extracted from the crust in the form of fossil fuels, coal, oil, and natural gas, represents a sudden re-entry of ancient solar energy into the modern system. These materials are the compressed, chemically altered remains of forests and plankton that lived hundreds of millions of years ago. To explain this on the fingers, a lump of coal is essentially a carbon battery that was charged by the sun 300 million years ago during the Carboniferous period. When we burn that coal, we are releasing the sunlight of the Paleozoic era back into the 21st century. This massive redistribution of carbon is creating a new geological marker, the Anthropocene spike, that will be detectable in the sedimentary layers of the Earth for millions of years. Future geologists will see this sudden shift in carbon isotopes as a unique and unmistakable signature of a technological civilization that moved the planet's carbon archive back into its active atmosphere in a period of only 2 centuries. As we look toward the ultimate legacy of the human species, carbon will likely remain as our most durable biographer. Even if our cities are ground into sand and our plastics are degraded, the massive quantities of refined carbon we have created, such as synthetic diamonds and carbon fiber structures, will persist. A diamond produced in a modern industrial press is chemically and physically identical to one forged in the mantle. It is a crystalline fossil that can survive the heat and pressure of the Earth's interior. Thousands of years after the decline of industrial society, these carbon-based technofossils will remain in the soil, providing a permanent and untarnished record of our ability to manipulate atomic structures. Carbon is the only element that can bottle the history of our technology into a form that is immune to the passage of time. The final chapter of carbon's role as the biographer of life occurs when the biological journey of an organism concludes and the element returns to the soil. In a natural ecosystem, the carbon in a human body or an ancient tree does not vanish. It is liberated by decomposers and returned to the cycle. It may become part of a new plant, be carried into a river, or be buried in a sediment that will one day become a new vein of coal or a new layer of limestone. This is the dance of the multiform god. The carbon that currently allows for the firing of neurons in a human brain was once part of a primeval forest, a volcanic plume, and a microscopic shell in a prehistoric sea. It is a material that is constantly being reincarnated into new roles without ever losing its fundamental atomic identity. We are merely temporary containers for a substance that has been circulating since the Hoyle Resonance first permitted its creation in a dying star. The story of carbon is therefore a narrative of profound and honest continuity. It is the element that turned the helium barrier of the early universe into an open door for life. And it is the element that ensures that the history of that life is never truly forgotten. Every breath we take and every word we write is enabled by the 4-electron handshake of an atom that has already seen the birth and death of stars and the rise and fall of entire geological eras. We do not own the carbon in our bodies. We are merely utilizing its unique ability to hold a shape and carry an energy before it returns to the planetary ledger. When the sun eventually expands and the Earth is consumed, the carbon that was once us will return to the solar atmosphere, eventually being scattered back into the interstellar medium. There, it will wait in the cold vacuum for the gravity of a new nebula to pull it into the formation of a new world. The biography of carbon does not have an end. It only has transitions. It is the multiform god of the periodic table, the silent biographer of the cosmos, and the only material that can honestly say it was there at the beginning and will remain at the end. Every pencil mark and every diamond is a testament to this permanence, proving that the most common and social element in the universe is also the most resilient and meaningful. We are a biological manifestation of a stellar lucky break, a carbon-based existence that is etched into the very fabric of time, moving forever through a cycle of creation that is as infinite as the stars from which we came.